I wanted to do a video in my Calculus Try It series where all of the different convergence tests for either non-alternating or alternating are all mixed together, and you have to pick which test will work and then if it converges or diverges. Pause here and try them, and then I'll show you my work. All right, if this video helps you, please like and subscribe for more of these Calculus Try It videos. I'm going to go through, and as I go through, I'm going to kind of erase them just to create more room for myself. And I may do some of kind of the shorter ones first, just so I can create room. So, for example, this one right here. Whenever you have a number to the nth power, if it's a number, and pi over e, despite what it looks like, it is a number to the nth. This is a geometric series. So I'm just going to put a little geometric right there. And a geometric series, the number in the parentheses raised to the nth, the number raised to the nth, has to be between -1 and 1 to converge. And of course, this isn't. So pi over e is bigger than 1. This will diverge. Okay. Next up, let me just kind of get rid of that so I have some room to work. Next up, we've got 4 over n to the 3/2. Whenever you have a number, just a plain number on top, and then on the bottom it's n to a power, this is what's called a p-series. And a p-series all hinges on that exponent. The exponent must be greater than 1 to converge. This is 3/2 is greater than 1. This converges. All right, next up, let's go to this one. Whenever you have a function raised to the nth, so not a number to the nth is geometric. This is an entire function. We're supposed to use the root test, okay, the root test. And the root test says, basically, take the limit of that function as you go to infinity. And of course, it's 3/5. So you almost treat it like it's 3/5 to the n. You're almost doing like a modified geometric. Well, that's a convergent series. So this will converge by root test. I'm sorry I'm jumping around here. Like I said, just trying to kind of create some space as I go. All right, let's go to the top one. I would use for this one a limit comparison test. Limit comparison. And I would say, well, the most powerful thing on the top, most powerful thing on the bottom, reduce n squared over n to the 4th would reduce to 1 over n squared. This is a convergent p-series, so this thing converges. There's more to the limit comparison test, evaluating the limit as you go to infinity so that these two, the original that I made and the comparison that I made, you can establish that they behave the same way. In the interest of time, I'm not going to do that, but you can seek that video out on my channel. Okay, so by limit comparison. Let's do another limit comparison problem. I see another one right away. Here we've got 2n. Here we've got n squared. So 2n divided by n squared would reduce to 2 over n. That is a divergent p-series. So this thing will diverge. All right. Okay, let's go to the top one now. I have enough room. N factorial over 4 to the n. Because we have a function mixing here, we've got some factorial on top and exponent on the bottom. I would use ratio test. Limit comparison, the one I just got done using, really works best for when the most powerful thing on the top and bottom are the same types of functions, and you can easily, just reduce them to a simpler series. That's not true here. So I'm going to use ratio test. So we do the next term. So just putting in n plus 1 divided by the original. So I'm going to multiply by the reciprocal. And I always just do this kind of reducing right away. I say, well, I've got one additional 4 on the top. N plus 1 factorial is the same as n plus 1 times n factorial. So that. So then I say, well, what I have left after I do my algebra is this. And your ratio that you created, you take the limit as n goes to infinity. Well, this is infinity. That's greater than 1. And if that ratio is greater than 1, you diverge. If it's less than 1, you converge. If you're equal to 1, now use the wrong test. You got to use something different. Okay, let's get rid of that. Let me kind of do some of the alternating series here. Okay, so when a series is alternating, it's got this -1 to the n, and it is alternating because it's not, it's being raised to just the nth power, not like n or 2n or something like that. We do 2 steps. First, we say, well, is the limit of that function, just don't worry about the alternating part, just say, is the limit 0? Well, yes, it is. So it converges. Next, we say, well, if I ignore the alternating part and just say, does that converge or diverge? Well, that's a divergent p-series. So this converges, but only conditionally. Okay. Now this next one, I'm going to leave these just, and I'll erase them both at the same time. So it's alternating, and again, just, make sure it's -1 to the n, so we're good. So the first thing we ask ourselves is just, well, is the limit of that part as we go to infinity, of the function kind of part of it, is that 0? The answer is yes. Higher powered thing is on the bottom. N factorial is more powerful than 7 to the n, so the limit is indeed 0. So we know it converges. Now to converge absolutely, we have to ask ourselves, or conditionally, excuse me, to know that we need to ask ourselves, would that series converge? Well, the test that's probably the most logical to use here is ratio test. That's the next term divided by the nth term, so usually we just multiply by the reciprocal. And I always just do my canceling, or my simplifying, I should say. I got an extra 7 on top. N plus 1 factorial is n plus 1 times n factorial, so I have that. Now, this is the ratio that's left, just 7 over n plus 1. I take that limit. Of course, 7 over n plus 1 as n goes to infinity, that limit is 0. Anything less than 1 leads to convergence. So this series would converge whether it were alternating or not, which means we say it converges absolutely. Okay? Now this next one, kind of again, it's alternating, so we say, well, the limit as n goes to infinity, 2n plus 3, 3n plus 6, well, that limit's 2/3. It's not 0. Well, this diverges. No reason to do anything else. Let's get rid of these things so that I can have some room for the last few problems. Let's stick with the alternating. I'll kind of work my way backwards here. This last one, we'll say limit as n goes to infinity, n squared plus 4 over n to the 5th plus 5. So you'll notice the highest powered thing is in the denominator, so the limit's 0. So we know it converges. Then we say, well, how about, the series, n squared plus 4 over n to the 5th plus 9. I would use limit comparison for this. I would say n squared over n to the 5th reduces to 1 over n cubed, which is a convergent series, p-series, so this converges by limit comparison, so converges absolutely. Now this cosine of n pi, I just for being simple, I didn't put the rest of the series stuff on any of these, but I did want to on this one, because think about, if this were cosine of 0, that's 1. The cosine of 1 pi is -1. Cosine of 2 pi is 1. Cosine of 3. So this right here, that is no different if you just want to say, well, what if I just said it's -1 to the n? It's the same thing, because cosine of pi n is simply alternating. So the limit as n goes to infinity of 1 over n is 0, converges, but that series diverges, so it's only conditional. All right, so let's finish with this last one. We have a sine squared of n over n squared. And my suggestion, whenever you have trig functions, I would bound them. I would think to myself, well, sine, of course, is between negative 1 and 1, but the minute you square it, you're between 0 and 1. So the numerator's greatest value would be 1. So 1 over n squared would always be greater than or equal to sine squared of n over n squared, because sine's maximum value is 1. Well, this is a convergent p-series, and if it's greater than this other series, this must converge as well by direct comparison. If this video helped you, please like and subscribe for more of the Calculus Try It series.